is the wind. Let's begin with a humorous but kind of peripheral quotation in a book about entomology, where the author expresses some surprise that bugs can fly. So, if you'd like to read more about wind after this lecture, here are two resources that I'd recommend. The first is a book by Eric Howe, Wind Turbine Fundamentals, Technologies, Application, and Economics. And this is really an excellent and very complete wind reference. And if you're more interested in recent trends in the US, this report by the EERE is excellent to get a sense of that. So first of all, what is wind? How do you think about wind? You know that the air is 78% nitrogen and 21% oxygen, plus some trace gases. And you know that because there's some temperature, the molecules are all running around. And you can calculate the speed with which they run around, and it's something like 1,000 miles per hour. You can also calculate the speed with which they run into each other, and it's something like several billion times per second. So the molecules in this room are in this constant state of motion. But aside from the vents on the ceiling, we might say that the air in this room is pretty still. So in what sense do we mean that it's still? So if we set up a little loop in the room and count the number of molecules going through the loop this way and the number going through that way, if the room is really still, we would find that the same amount of mass flows through the bottom as it flows down to the top, with some small fluctuations. But when there's wind, there's some net flow of mass, some net flow of molecules through some region. So to make it a little bit more quantitative and get a sense of how much mass flow there is to think about the wind that way, let's think about some area A and wind moving at velocity v, which will cross through that area A. So in some time, delta t, that wind will be able to move the distance v, the velocity times delta t. So the little cylinder of air that will go through some area has a volume, which is the area times the velocity times delta t. Now, for the rest of the talk, I'll denote the mass flow rate as m dot, and this is somewhat customary. And you'll note here that if you know the volume of the cylinder and you know the density of the air, you know the mass of the air in the cylinder. And you can find the amount of mass per second flowing through that area by just dividing by the delta t. So you know that the mass flow rate is the area times the velocity times the density. And if you just put some maybe more practical numbers to it, the wind speed in, say, miles per hour in an area in square feet, you multiply that by 0.1 to get the number of pounds per second flowing through some area. So if you put a door frame at the top of a hill, and there's 10 mile per hour wind blowing through it, that's 18 pounds of air per second. So that's how to think about the mechanical sort of power embodied by the wind. That it's some flow of mass through some surface area. So just to revisit some of your intuition about the wind, well, you know that the wind embodies some energy, because if you drive around in the country here, you might see these old these water pump turbines. And you know that to lift water from the bottom of the reservoir to the spigot with some mass over some height, so you know that the wind is somehow doing work, so it must embody some energy. You also know that you have to brace yourself to stand in a gale force wind, or if you run or bike into the wind, it's much harder than if you bike with the wind toward your back. So that the wind must embody some force. So here's a little device which I made, which is really a pretty rough approximation of what might be happening. But in this, rather than a continuous stream of wind, we have some balls that are thrown at some rate, and they have some mass, and this device catches them. And with each ball, it ratchets over, and eventually the ball falls out the bottom. So recall that the kinetic energy embodied in this moving mass is 1/2 the mass times the velocity squared. So that each time this device catches one of these balls, it can sort of inherit that amount of energy. device, that would be some amount of energy, there would be some rate that this device would be receiving energy. And you can see that that's the mass flow rate times 1/2 v squared. So, of course, the wind is a much more continuous phenomenon, not so much individual masses impacting some object. So we can plug in the form of the mass flow rate that I showed in the previous slide, which is that its mass flow rate is the density times the area times the velocity, and find that the power embodied in the wind is 1/2 the density times the area times the velocity cubed. And I think the really important thing to remember here is that the power embodied in the wind scales as the velocity cubed. So a 16-mile-per-hour wind really has a lot more embodied power going through some area than a 1-mile-per-hour wind.
What is rho?
Oh, sorry. So rho is the density.
Yeah.
Okay, so that's from the viewpoint of energy, but you can also think about it in terms of the momentum. So this mass moving at some velocity v will have some momentum, its mass times the velocity in v. And you know that when you catch a ball, you feel kind of a jerk. And if you were to say catch objects at some rate, you would feel something like a force. So to make that more definite, the force is the rate of momentum exchange. So in this case, it is the rate that this device is receiving momentum from these objects. So again, it's just the mass flow rate times the velocity. And if you plug in the mass flow rate, you find that the force is proportional to the density times the area times the velocity squared. Now, for a given object, well, so this really has something intrinsically to do with the air flowing through some area, whereas the force on an object really has a lot more to do with the object itself. It's less intrinsic to the air. That is, if you put a big square in the wind, it'll feel a lot of drag. But if you put some aerodynamic teardrop shade, say, it will feel much less drag. And the way that's encoded here is that you multiply it by this dimensionless drag coefficient. So for something like a square, this is close to 1, and for aerodynamic shape, this might be 1/10 of that. So the force is proportional to the velocity squared and this dimensionless coefficient. So there's not just a force in one direction. There's a force that you're familiar with in two directions from having your hand out the window of a moving car. So you know that if you tip your hand at some angle, you feel not only a drag from the wind, but you feel a lift, and that's perpendicular. So if the wind is blowing in this way, the lift is perpendicular to that. And you know that the ratio of the lift to drag changes as you change the angle of your hand. So you can use either the lift or the drag to make a wind device, and the first types of devices that people made were based on drag. And this is a 19th century Persian windmill, and I believe they originated at least in the 9th century, or that's when they were first recorded in Persia. And the idea was that you'd have a wall, an earthen wall, and then these rotating vanes, and the wind would just blow through. And the drag on these vanes would induce rotation in this. But note that this can't spin faster than the wind. Also note that doesn't really look like a modern wind turbine. These look more like the wind turbines you'll see in the fields today that generate electricity. And these might not make a lot of sense right away because, well, from the point of view of imagining your hand out the car window, these seem to have sort of a flat hand to the wind. You might think that you should have vanes that are aligned more or less along the direction of the wind, but maybe tilted to give you some lift. But instead, you see that these look practically flat. So I want to spend some time talking about how to think about these lift-type turbines, because the mechanism is a little bit more subtle than drag, which I think is a lot more intuitive. So just to connect to the first 3 lectures, the idea is that you can produce rotation in one of these, and you can use that rotation to induce a voltage to produce electricity. So, in lectures 1 through 3, I talked about how to use electrodynamics to make motors and generators. And the idea there was that if you had a changing magnetic flux through some circuit element, that you could induce a voltage. And if you weren't at the first 3 lectures, I'd be happy to explain that afterward. So you see that a modern generating turbine looks something like this, where there's a generator up on the tower, and it looks in some ways like the Dutch-style mill rather than the drag-type mill. So this is it's based on the principle of lift. So that principle is what's inherited by aircraft. So a good way to start to think about how these things work is to think about an airplane wing. So if you look at some segments of an airplane wing, there's some incoming air, and there's some sort of chord line at this wing, and there's some angle that this thing makes with respect to the incoming air. And with that, you can produce various amounts of lift or drag. So now if you were to sit in the middle of this turbine and look down at the blade, and look at a cross-section of that blade, it would really look something quite a bit like an airplane wing, though the designs are quite different these days. But so the point is that the wind, the ambient wind, seems to blow against the flat side of this, that it seems to have its sort of hand flat to the wind. But you also note that if you were to ride on the tip of this blade, you would feel some additional wind just by virtue of its rotation. So there's some additional incoming wind in this direction. So that you get an effective, or a resultant wind, which is much more along the line of along this airfoil.
Yeah. Which has the greater effect, or is there a difference if the incoming wind is in turbulent flow or laminar flow?
In this case, you want as laminar as possible.
Laminar.
Well, so you just want some.
All right, and going back to the World War I fight, using wings as a director, why did that not increase the force on the blades?
Well, maybe we should talk about this afterward.
Oh, okay.
I want to kill me through. But yeah.
I take it there are equations that handle this problem.
This one, yeah. So there's some resultant wind, and the airfoil makes some angle with respect to that. That's this attack angle. Now, in turbines, there's an additional angle, and that is that this thing is rotating in some plane, and there's an angle between the plane of that rotation and the chord line, and that's called the blade pitch. So let's go back to this picture of the hand. So again, you know that if you have your hand at different angles, you'll feel a different amount of drag versus lift. And the force of the drag, again, is proportional to the density times the velocity squared times this drag coefficient. And the lift looks practically identical, except you have a lift coefficient. And you see that the difference in the amount of lift and drag, as a function of this sort of attack angle, is manifest in the difference in these coefficients. So you can plot the amount of, you can plot this lift coefficient, this is the blue line, as a function of the attack angle, and the drag, the red line, also as a function of the attack angle. And you see that for a small angle of attack, there's very little lift or drag. That is, if you have your hand just along the line of the wind, you don't feel a lot of either. But then at some intermediate angle, say around 5 degrees, you get a significant amount of lift compared to the amount of drag that you have. So that means that the lift force is much, much greater.
Sorry to
So at some point, you also know that if you tip your hand far enough, you get less and less lift, and that's called stall. So above, say, what is this, 17 degrees here, the lift goes down. We also know that the drag is increasing more sort of quadratically, and eventually it's a similar magnitude to the lift. So now if you do this analysis for the wind turbine section, you see that there's some big component of lift and some smaller component of drag, and that the drag is along the direction of the resultant wind velocity, and the lift is perpendicular to that. We also know that the blade is constrained to move in a plane, so all of this lift is really, or a big part of this lift is out of the direction of that plane. And the thing that really matters is the component of those forces that are in the plane of rotation, because that's what provides the torque for the spinning blade. And you see that if you project the drag and the lift into that plane of rotation, there's still more lift than there is drag. So that means that there's some net torque which would like for your blade to spin up, to spin faster. So that's the basic operating principle of a lift type turbine. So that was just one segment of the blade, but if you look along the length of the whole blade, you see that there's some distribution of force. So say in the middle, there's a little bit more force. And you have some axial force. Again, that's out of the plane of rotation, so that's just some mechanical stress. And then you have some tangential force, and that's what actually produces the rotation and the torque, and that's what you use for the generation. One thing that's interesting about these, which you should note, is that they can spin faster than the wind. In fact, many of these have a target to spin, well, if you look at the tip of the blade, they have a target to spin 7 times faster than the wind. And so that's really a significant difference with the drag type, or between this and the drag type turbine. So this is called a horizontal axis turbine because the axis is horizontal, HAWT sometimes. They're also vertical axes, or vertical axis turbines. One disadvantage of this is that you need to so-called yaw the wind. So if the wind is blowing in this direction, you have to be pointed in that direction. If the wind changes, you have to repoint the turbine. So let's think about how much power such a device can extract from the wind. So I said that the power embodied is the velocity cubed. And you might think that what you want to do is build a device that takes wind of some velocity v and slows it down to 0. That is, it takes somehow all the energy out of the wind. So say you produce such a device, you put it on some mast and you put it inside some box. So there's some black box that takes the incoming wind, takes all the energy out of it, slows it down to 0 velocity. Well, if it's 0 velocity on the backside of this box, you could just close the box or do something. But then you have the problem that if there's no flow out of the back of the device, you can see right away that it's hard to imagine flow going into the device. So this type of device, which would hope to extract all the power from the wind, you see it really kind of impractical. So let's think about how to make that more realistic. So you know that with a river, if you have a very fast flow, it can go through a narrow channel. And if you want to slow that flow down, you have to allow it to go through a much wider channel. That's really a similar kind of thing with the wind. That is, if you want to take some velocity out of the wind, so here's the cross section of the turbine, and here's the tube of wind moving toward the turbine, and here's the wake of wind exiting. If you want to extract power, the velocity here has to be less than the input velocity. But you also know that if you have a ton per second of air blowing in this side, you have to have a ton per second of air blowing through here, and a ton per second blowing through this output surface. So that the mass flow rate at each of these points has to be conserved. And what that means is that if the velocity decreases, like on this output, the area has to increase. So you go from, you have a small input surface area increasing slowing down when it hits the turbine, and then increasing further still in the sort of weight. So from this, you can start to see why this picture is making less and less sense. So in the notes, I put a more technical derivation of the Betz limit if you're interested to read more about this. But there is a fundamental limit on how efficiently you can extract mechanical power from the wind. And you can derive it just using energy and momentum conservation. And it's called the Betz limit. So you can find the total power extracted by the wind, extracted by the device, and you can find the total power embodied by the wind, and take the ratio of those. And that tells you how effectively you're extracting the power from the wind. And that's called this Betz efficiency. And again, there are the details of this in the notes, but this is the conclusion, and you can really kind of summarize the intuition about this. So there's one term which is due to the energy, and there's one term which is due to the mass flow. And if your goal is to maximize the efficiency with which you extract the power from the wind, you like to maximize with respect to both of those terms. So let's think about just the first term. So this is 1 minus this quantity squared. So to maximize this term, you want to make this as small as possible. So in particular, this term would like to see the output velocity be 0. And from the point of view of energy, that's what makes most sense. You want to take all the velocity out of the wind and convert it to energy. But this term, which has to do with the mass flow, this is maximized when there is some output velocity, which is to say that to extract the power, you have to have some flow through the device. So you have these two competing terms in the efficiency, and you can maximize this, and you find that the maximum is at 1/3. So that is, if you have a 30-mile-per-hour wind incident on the turbine, that you want to design things more or less so that you have a 10-mile-per-hour wind on the output of the turbine. If you plug this into the efficiency expression, you find that the maximum efficiency with which you can extract the power from the wind is 16 over 27, which is kind of an neat magic number, or about 60%. So just based on momentum conservation, there's an upper limit on how much power you can extract with some mechanical device. And you note that this, from the notes you'll see that this doesn't depend on there being even a particular type of turbine design. It's a pretty general statement. So these have been kind of more abstract observations about the energy in the wind and how much you can extract from it in theory. So let's think about some real turbines. First of all, they're very big. This is the mast, and here's a little man inside the cell, and here's a generator that's being mounted. And then these are some sort of typically sized turbine blades. So you can see going through the town in England. And you can see that the scales here are really quite large. So there's a study by Lomborg in 2001. So these things, in that these turbines are so large, there's some concern not only that people maybe think that they intrude on a view of some planes, but also that they can kill birds. Well, there's a lot of installed wind capacity in Denmark, and this is a study by Lomborg in 2001 that tried to estimate the number of birds that were killed by turbines compared to cars and cats. And this is colorfully illustrated in this book, Sustainable Energy Without All the Hot Air. And if you're interested in sustainable energy, I'd really recommend having a look at this. This is a free book that's available online, and it's written by a physicist.
Birds are all Christian.
Sorry?
Birds are all Christian.
Yeah, and you also would maybe think that maybe you should put buildings on here, because you know that birds run into windows also. I'm not sure how that stacks up compared to these other causes. But at least in Denmark, with the installed capacity, you see that it's not significant. So that Betz limit was the efficiency, some sort of spherical cow efficiency limit, just based on physics, let's think about a real turbine. So this is, so this is a little bit small to read. Okay, so again, the maximum power, mechanical power that you can extract from the wind is about 60%. And in this well-designed real turbine, you see that it's something like 44% of the power of the wind that's extracted. So if you have 3 megawatts of wind power subtending the area of the turbine, this particular thing is extracting 1.3 megawatts. Now, that mechanical power, of course, has to get converted into electricity, but let's go through the different steps here. Well, you have some bearings, and that's 99.6% efficient. You have some gearbox, some generator, and so these are the generators that I talked about in the second lecture. And then you have some conditioning that makes the power more amenable to the grid, and the output of this whole chain is 1.2 megawatts, and you see that the overall efficiency is about 40%. So, in going from here to here, you lose very little of the mechanical energy. So this step of the chain is really quite efficient, and it's the step in converting the mechanical power embodied in the wind to mechanical power rotation that is dominating the losses. And then, of course, you have a transformer that puts it onto the grid. So the Betz limit that I described just has to do with momentum conservation, but you also know that you have to conserve angular momentum. So in particular, if you have some stream of air, some stream of wind flowing at your turbine, if it's causing the turbine to spin, then there's some angular momentum that's being exchanged, and to conserve it, that means that the weight has to have some spin, and to do that takes some energy or some power. So the amount of power that this thing, a rotating turbine, can extract is less than what you think or what you would calculate from just the point of view of momentum conservation. And in addition to that, you also have vortices produced at the wing tips and at the hub, and to produce those structures, again, takes some energy. So both of those sorts of effects depend on how fast the blades turn. So we're trying to get to a more realistic picture of how efficient these objects are. Okay, so here's a really neat figure from this book, which I told you about in the introduction. So at the top here is the Betz limit, and this is just sort of a momentum theory. Now, if you include the spinning weight, you find that, I should say that the x-axis here is the tip speed ratio. So this is how fast the tip of this blade is moving relative to the incoming wind speed. So say right here, if the tip speed ratio is 10, that means if you have a 10 mile per hour wind blowing at your turbine, the tip of this blade will be spinning at 100 miles per hour. So this is really moving quite a bit faster than the wind. So if you plot the efficiency as a function of that tip speed ratio, you can get a sense of the physics of the conversion. So, so the first thing to note, or one thing to note, is that the efficiency improves as you add more blades, but not maybe as much as you'd think, and that's because these spin faster. And you also note that if you added one more blade to this, you say, well, why use 3 and why not 4? Well, you only get a kind of a few % gain in power. And from the point of view of, well, minimizing your cost, you see that if you have 3 blades and you add a 4th, you have to pay for a whole 4th blade, but you're not gaining a lot in power. So this is really a convenient sort of physical optimum and an economic minimum. And you can see that these older designs, like the wind vanes on farms, the Dutch windmill, and these sort of drum-type bigly drag mills, are significantly lower efficiency, and they have much lower tip speed ratios. do with the wake. And you also know that these real turbines have to drop off on this side as you go to higher tip speed ratios. And the reason for this is what I mentioned in the previous slide, which is that you can have vortices and drag and various terms. And those really start to pick up when the faster these things spin. So that's one of the things that can cause the loss on that side. So for each design, there's really an optimum tip speed ratio, and you have to think about that in terms of the power you want to generate and the site.
Question. At a ratio of 6 and 100 mile an hour wind that comes along once in a blue moon, you've got a tip speed of 600 miles an hour.
Yeah.
Are these, do these blades rotate so that they...
Exactly, so that's a great segue into this slide. Yeah, so you have mechanical ratings and electrical ratings on your generator. And for a given site, you put a generator in with some finite rating, and you don't want to exceed that, like say, you get gusts or even moderate speed winds, because the power body goes as the speed cubed. So you really start to get significant amounts of power. So in normal operation, the wind is blowing in this way, and one thing you can do if you don't want as much power, you can change the attack angle so it's effectively zero, and that really drives the lift down, and that manages the speed of your turbine. Now, if the wind keeps on getting faster and faster, you can continue to rotate until you're in sort of a feathered position where you have a flat surface against the direction of rotation, and that effectively breaks the structure. Another approach is to increase the angle of attack. And when you do that, recall that at some point the airfoil goes into stall. And one thing that's neat about this approach, which is exploited in a lot of Danish designs, is that you can have a fixed blade pitch, and as the wind gets fast enough, the resultant wind vector here is enough for the airfoil to go into stall automatically. So you don't even have to change the pitch. But it's much more common these days to have something that uses this type of mechanism. The other thing you can do is simply turn out the wind. So instead of going in the direction of the wind, you can just point the other way, and that's called furling. So as you can guess, the power produced by a turbine varies as a function of the wind speed. So for some low speeds, there are losses, and it's just not efficient to start. So no power is produced. And then there's some cut-in velocity where you start to produce electricity, albeit very little. And there's a partial load curve where the output power rises rapidly. I think it's something like VQ in principle, as the wind speed picks up. And then once you reach the rated power, you can use these other mechanisms to keep the output, say, at 3 megawatts, regardless of how fast the wind is blowing. And this is a very typical curve that people design for. And then at some point, you just want to go into a safe mode when the wind is blowing fast enough that you don't even bother generating electricity. You just try to maintain the integrity of the turbine. So all this discussion really has to do with the wind fluctuating, and you need to have a good way to quantify how much that fluctuation is and to understand that aspect of the site. So you can plot the probability distribution of a given wind speed, and these dashed lines are the relative probability. So this just says that on this site list, it's most likely that you'll have wind speeds of around 7 meters per second. Whereas, because you see this curve is much lower out here, you're less likely to have gusts at 20 to 25 meters per second. So this just says that most of the time you have consistent wind, and then you have some gusts. Often you don't see this as a relative probability, but you see it as a cumulative probability, and that's what these solid lines are. So let me explain how this works. So take this point. You see that this is at 0.8, 40% of the time the wind speed is less than 10 miles per hour. So if I went to that site and took my anemometer and measured the wind speed, 80% of the time I measured it will be less than 10 meters per second. Likewise, down here, this is at 0.4, so 40% of the time the wind speed is less than 5 meters per second. So this type of curve encodes the distribution of wind speed in the site. Likewise, down here, when it's practically 1, that's to say that almost 100% of the time the wind speed is less than 25 meters per second. That is, it's very rare for it to gust up to 30 meters per second. So if you know the power produced at a given velocity and the probability that you have a given wind velocity, you can find that you can estimate the total power that the given turbine will generate at a given site. And this particular plot is called the graded annual power. So what this is the time, and you'll see that this is 1 year. So these are all the hours in a year, and the year is about 8,800 hours. And this is the power that you produce for a given amount of time. So for, say, 2,300 hours, the turbine produces its rated load of 3 megawatts. Whereas for a couple thousand seconds during the year, it produces some partial load power that's less than 3 megawatts. You can also see that for about 2,000 seconds between here and the end of the year, the wind isn't blowing fast enough to produce any power at all. So this distribution goes to 0. This combines a couple of different things. Is this clear to everyone? So when you talk about how effective the turbine is at a given site, you want to have some kind of average statistic. And a good one is of course, the average annual power, how much you expect to produce in a year, but also the equivalent full load hours. And this is the amount of time that if the turbines were running at its full capacity, that it will produce the same amount of energy that the real turbine did in 1 year. So this tells you effectively what fraction of the time it's working at effectively its full capacity. So if you compare that to the total number of hours in a year, you see that it's maybe 40% of the year that it's effectively working at full capacity. So more about real turbines. So this is from the second report, and these are installed. This is installed capacity in the U.S. So you see that. So this is the year, and then this is the capacity or the rating. And so you see that early on there's an emphasis on these smaller turbines. So if you go in California, you see some of these smaller type of structures that are between 0.5 and 1 megawatts. And then it became more popular to install these megawatt scale designs. And then today, well, kind of today, you see that that blades between 1 and 2 megawatts are common. So these are really quite large. So how do the different states compare? Well, here's Texas, and you see far and away Texas has the most installed wind capacity in the U.S., almost twice as much as California. And so, yeah, followed by California, Minnesota, Iowa. And you note that Illinois is not doing too badly. I was surprised to see that it was above Oklahoma, because I thought Oklahoma was a big wind state also. But then if you look at the total fraction of the in-state power, you see that Minnesota and Iowa are really doing quite well at around 7.5%. So while Texas produces so much, it has so much installed capacity that also requires a lot more electricity than Iowa and Minnesota. And you see that Illinois is pretty far down the list at about 0.8%. So this shows the how well different states are doing. To see that these are states with more than a gigawatt of installed capacity, and so Texas and these states, and California, and there are many states which have less than even 20 megawatts. So just to put this in perspective, though, here's a plot that I showed last week. These are the primary fuel inputs. And here are the different points of consumption: residential, commercial, industrial, transportation. And here's electrical generation. You see that, I'm sorry this is hard to read, but wind is 0.51, whereas the total of electrical generation is about 40. So you see that while it might appear that there are a lot of installed gigawatts, that's really a small fraction of our electricity in the US.
What are the units?
Oh, sorry, these are units of quads. So this is a quadrillion BTU.
Oh, okay.
Yeah. And it's a little bit tricky because these are thermal, obviously, and then this is a mechanical, so it's a little bit subtle. But there's something to be optimistic about, and that is that the cost of wind has really dropped, and because of that, the installed and another reason is the installed capacity has really been rising rapidly in the last 20 years. And a lot of this price drop has had to do with pretty aggressive policies in, as far as I know, in Denmark and Germany that have driven prices down. So you might say, well, maybe that trend will continue, and how much power can we actually extract from the wind? How much power is there available? Well, wind is fundamentally due to incident solar power. It doesn't just blow around for fun. So you have to have some incident power that makes its way to the surface, and then some amount of that is converted into wind. And some amount of that is wind that is below 1 kilometer. And some amount of that is wind that is on land. And then some lesser amount is wind that's available near the surface. So this is if you covered the entire land surface with wind turbines at 100% efficiency and basically extracted all of the wind energy over the land surface. So you see that's optimistic. It's been estimated that something like 2 terawatts is a more sane limit, but that's still a remarkable amount. In terms of the total amounts of power that you need to replace other forms of energy, it's about 10 terawatts. So first of all, this is highly optimistic, and you see that the needs are quite great. So just to wrap up, so wind, the way to think about wind is it's a flow of mass, and it embodies some power that scales with the velocity q. And you can either use the force, the drag force, that's what was used historically, by historically a long time ago, or you can use lift, and that's much more the modern way. And but any way you extract power from the wind, there's some fundamental limit to how efficiently you can extract that power, this Betz limit. That's around 60%. But moreover, as you point out, there are limits to how much power you even want to extract, because, well, your generators and your mechanical structures have limits. So rather than this Betz limit may be a fun thing to think about, but in practice, you also have mechanical considerations. And because of that, these turbines have a standard power curve where they reach some rated output. And based on that power curve and the probability distribution of the wind speeds, you can come up with statistics about how effective a given turbine is at a given site. So I just want to show this picture for topic in lecture 6. My other car is a sphere, so there I'll talk about drag in automobiles. So you can calculate how many miles per gallon you should expect to get just based on the drag force. certainly a lot of this inherits itself from sailing. Is furling the sailing term?
I mean, there's a lot of angles on sails that I've heard they're putting rotors on boats now.
Oh, really? Huh. I don't know. That's interesting, though. Yeah.
I've gotten now confused on the essential kind of the fundamental concept of drag and lift. Before this, I always took the drag as being related to a vacuum behind the hand, for example.
Yeah.
And the lift related to the different on an airfoil to the difference in pressure because of the length of the cap. But with your drawing, it seems like there's also a component of just the kinetic energy of the wind particles hitting the underside of the hand. Is there, am I missing anything in this one?
Yeah, well, so if you take like a ball, if there weren't any drag, the flow would just go around, and there'd be some pressure from the incoming wind, and there'd be some pressure on the backside, so that there'd be no net force on the ball. But what happens in reality is that the flow separates, and you get this, you get sort of turbulence impact. And because of that, you have an asymmetric force on the ball, which is what's manifested as the drag.
So it's a combination of all those factors. The kinetic energy and the suction, let's call it, the net quality.
Yeah, and also well, the airflow, the fact that you're directing mass.
The wind turbines that are being produced now, the biggest ones, are absolutely monstrously huge.
Yeah.
What is the nature, where is the cost-benefit, what is the cost-benefit advantage to huge turbines? Where does that emerge from?
Yeah, so I think from a fiscal point of view, there's something, just like based on the cost of material of the turbine, I think there's an argument that you want to have smaller turbines. But the model in utilities is that you can have economies of scale, and I think you also have higher efficiencies of all your mechanical components and generators.
Have you seen any graphs of cost per kilowatt based on size?
I haven't, but I'm sure I could try to find one.
That would be interesting to see, because that's really the destructive part of use and everything else that people are concerned about, in part bears on the size. These things are monstrous.
Yeah.
There's space too. There's space, how much space they take up, how much land they're going to eat.
Yeah, well, the total land actually would be probably not changed that much, but
Not
you're
true.
building.
No, you have to have access roads.
Yeah, but I mean, if you're going to produce the same amount of power, you're going to need a lot more small ones.
Yeah, you take up a lot more land with the small ones.
Okay, so the big ones have land conservation.
Yeah.
On your map that showed wind power generation by state, it looked like the southeast had almost none.
Yeah.
And is that due to the relative price of coal and oil and putting up a turbine, or is it political?
I'm not sure what all the forces. I think there are numerous forces that drive that. And I mean, obviously, a big one is having a good resource. So Texas and the central states have a better resource than the southeast. But yeah, I don't have a short answer to that. Yeah.
Are any windows that can be built to convert the wind directly, to lift water, or for any similar purpose?
Well, I mean,
Give it up on it.
I'm not sure. I mean, certainly historically, on farms to get water, but
In Holland, do they convert to electricity before they pump water?
oh, sorry, in Holland.
In Holland, yeah. I mean,
Oh, yeah.
water.
That's a good point. I don't know. Yeah, I could take a look into that. Yeah.
The other gentleman's question, southeast has not, you notice Texas, most of your installations are 300 miles inland from the Gulf. They can't build it strong enough to stand the hurricanes when they come. That's
of these states that you might suspect could do a bit better.
They get hurricanes too.
Yeah. That's what, yeah.
Any thoughts about windmills over the jet stream, about the surface of the earth?
Oh yeah, people talked about these sort of height generators, and I mean, it seems like you would incur a cost just by by doing that. So I don't know enough to compare and contrast the cost.
I've always worried about whether there would be a climate effect if you had enough windmills. Is that
I wondered about that, and I haven't ever read anything about that. And I mean, yeah, certainly if you somehow extracted all of the surface winds, you could imagine some climate effect. I would have to look around, but I didn't see anything about that aspect. It's interesting though.
When you see windmills, you see them spread out.
Yeah.
I take it from this that the fact that they reduce the rate of downstream wind, that calculations go into seeing what the overall spread will benefit. They could obviously be placed much closer together.
Yeah, there are a lot of studies that look at